Transformations of functions are looking at common functions that we know and moving them around the coordinate plane. We're going to look at how we do that, what parts of the equation cause certain things to happen, and stretching, reflecting, all of those things. You can see those objectives up here at the top. So let's take a look here. This comic kind of thing here probably will make much more sense after we go through the material. So I'm going to just kind of skip over it. You can kind of flip back to that once we work through some things. First thing we need to know is what would be considered standard functions. Sometimes these are called parent functions. The constant function, f of x equals a constant, some real number, is just a horizontal line, y equals c. We saw that back when we talked about horizontal lines. The domain, all real numbers, you can put anything in for x, although there is no x there, right? The range is only c. The only y value that you get out of this is c, and this has even symmetry. Notice it has y-axis symmetry. If we fold it on the y-axis, it has y-axis symmetry. You have same picture matching up if you fold it on the y-axis. The identity function, this is the line y equals x, using function notation, f of x equals x. This is the line with slope 1 and y-intercept 0, so it goes through the origin and has slope 1, so it sort of cuts the first and third quadrant equally in half there. And then the odd symmetry has that idea of origin symmetry, where you rotate it 180 degrees and you get the same picture. So that is the identity function. Absolute value function, no matter what x is, y is always positive, so that's this range, or always non-negative, technically. Even symmetry, because you fold it on the y-axis, you get the same picture on the right and left side there. Couple other important functions, the standard quadratic function. So f of x equals x squared. We're going to study quadratics in detail in the next unit. But this is a standard parabola, we call that. Square root function, and you can see here domain and range for all of these. This quadratic has even symmetry. The square root function has neither even nor odd symmetry. Cubic function looks like this. So when we cube the x values, what do we get? And you get this sort of S-shaped thing, and then a cube root function. So you can kind of look over all of those. Thanks to my colleague Dan Kernler for those graphs. They're pretty nice and helpful. Okay, let's talk about transformations of functions. The first type of transformation we are going to talk about is a translation. We have two types of translations. One is a vertical shift, up or down is what we're talking about. You take the whole function, the whole graph, and you move it up or down. That happens when you add a positive number to the function, outside the function. Remember, this is like a y, right? So if you take the y value and you add a number to it, it's going to shift the whole thing up and has no impact on the x value at all. Same thing here, if we subtract k, a number, from the y value, it's going to take the whole picture and move it down. So that's why y, adding or subtracting a number outside of a function, changes it by shifting it up or down. Here are a couple of examples of this. Notice this plus 2 is not inside the square. It is outside the square. So this is the standard parabola, that quadratic function, shifted up 2. Every point, it's kind of like think of taking that parabola and just picking it up and shifting it up 2 spaces. Let's go back up to that parabola here, the standard quadratic function. This is the parabola. That's what we call that. And this vertex, this lowest most point, just moves up 2 spaces. And every other point also shifts up 2 spaces. Take that whole thing and move it up. Here, this square root function, that's the parent function, square root function, and that -3 in that position shifts it. So it's a square root function shifted down 3 spaces. So that means we're going to take this square root function that we have here. This is actually half of a sideways parabola, and we shift it down 3. This point 0, 0 is on that function. It's a little hard to see, but if you plug in x equals 0, you do get y equals 0. That point would shift down 3 spaces. The whole thing would move down. Notice that when you make a change like this, you're impacting the y values. It can and will change the range of the function. You're changing the y's. The other option is if you want to shift left or right. The way we do that is we make a change to the x. So the x's changing are a left or right shift. This one is a little different because when you add k to the x value, you kind of would expect a right shift. But what happens is we need to sort of counterbalance what's happening inside the function. And so it's the opposite of what you would expect. Adding a positive number shifts it left. Subtracting a positive number shifts it right. This function, see how this is different. Up above, we had f of x equals x squared plus 2. Now my plus 2 is on the x before the squaring. So that is this horizontal shift. So this is the standard parabola. Shifted left 2 spaces. Okay, let's talk a little bit about why that's left instead of right. The idea is that if I plugged in x equals -2, it gets me to the same place as if I plugged in x equals 0 in the standard parent function. So x equals -2 corresponds to x equals 2 in the original. So that's why it's that shift to the left. It's sort of counterbalancing what you would expect. This is the square root function. Shifted right 3 spaces. Okay? As opposed to what we saw before, g of x equals the square root of x, and where the -3 was outside the root. Now this is inside the root. It's that impact on the x. This was a downward shift. This new one is a right shift. Let's talk about this. For me, the best thing to think about is what is the parent function. In this case, that is y equals the absolute value of x. That is, when you strip all the numbers away, what do you have left there? Y equals the absolute value. Then I'm always thinking about order of operations. So if I plugged in a number for x, what would I have to do first? Well, I'd subtract 4 from it, right? And that is a right shift 4 spaces because it's inside the function. It's inside the absolute value. That's the left or right. The fact that it's -4 means we need a right shift. Then, well, then you do the absolute value, right? That's the function itself. The plus 3 is an upward shift, 3 spaces. So I'm going to think about, first of all, what does the parent function look like? I am going to graph that in this blue color, and then we'll actually graph our h of x in a different color. The absolute value function, you can see it up here if we were to scroll back up to the absolute value. It's this V kind of shape. But if you don't know that, that's okay. We can kind of think about what that is. You should start to get familiar with and recognize what the absolute value function looks like, what all of these functions look like. You should know those. But you can kind of think about, okay, if x equals 0, y equals 0. If x equals 1, y equals 1. If x equals 2, y equals 2. And so on. So that's where that's why we get this V shape here. Because when the x values are positive, you get the exact same y value. When x equals -1, y is +1. X equals -2, y is +2. When you take the absolute value, it gives you that positive. So that is why we get this V shape. It's really two different lines there. Now let's talk about shifting right 4 spaces and up 3 spaces. Let's go to orange here. If I want to shift, and I could do this in 2 separate steps if I want, but I think with just translations, the shifting left and right and up and down, I think we can do it in 1 step. I'm going to take my point of my V here, shift it right 1, 2, 3, 4, and up 3, 1, 2, 3. That's going to be here at this point 4, 3. Now, if I think about moving this point right here, right 4 spaces and up 3, it's going to be in this position. The relative position to one another is still the same, right? So all of these points, as they get shifted, we end up getting this line that's parallel to the right side of this V. If I think about moving this point that was at -1, 1, I move that right 4 spaces and up 3 spaces, it takes me to here, and here, and here, and so on. And you get the other side of the V. So we literally just picked the blue graph up, shifted it right 4 spaces, shifted it up 3 spaces. That's how we do translations of functions. We could do this with any parent function. If this were different, the process is still the same. We have to pick those points up. These ones that I've plotted here are sort of our key points, but obviously x could be 1/2, then y is 1/2. That's why we connect the dots, and all of those points get shifted. Okay, let's do reflections. We're actually going to look at several transformations here, but I think we'll do the reflections, and then we'll talk about the, then we'll take a little break because this video could get super long because there's a lot with transformations. When you have a function outside, with a negative outside of the actual function, that is a reflection over the x-axis. So this function, f of x equals -x squared, that's a negative outside of the square, right? Order of operations would tell us if we plugged in a number for x, we would square it first and then do the negative. Well, because of that, we know that that negative is outside of the square. So because of that, we're going to reflect that standard parabola over the x-axis. So it's going to be a parabola that opens down like this. Okay, just take that standard parabola, flip it over. Now, the y-axis reflection happens when you put a negative on the x itself. So this example, the square root of negative x is a reflection of f of x equals the square root of x over the y-axis. You may be looking at that and saying, wait, we can't have a negative inside a square root. Well, you sure can if the x values are negative, so that now you have negative of a negative number. That's why we get this reflection over the y-axis, because you're changing all of the x values. So this would be, that would be the square root of negative x. Plugging in negative x's is okay there. This is y equals square root of negative x. This is y equals negative x squared. So the difference here is where that negative is. If it is on the outside of the function, like in this first example, it reflects over the x-axis. So anything that was below the axis would go up. Anything that was above the x-axis would go down. Same thing with this reflection over the y-axis. Anything to the left of the y-axis would reflect over to the right side. Anything on the right side of the y-axis would reflect over to the left side. Let's take a look at this one. Graph g of x equals negative of the absolute value of negative x. Well, our parent function here is the y equals the absolute value of x. All right, if you strip away all the numbers, you got some negative ones here. Strip those away, you get this parent function of the absolute value of x. Now, I always am thinking about order of operations. So if I plugged in a number for x, what would I have to do first? I'd have to deal with this negative first. The negative on the x is a reflection over the y-axis. That's this idea, right? If you have a negative on the x. Now, let's talk about this negative, because that's what we would do next. I mean, you do the absolute value, which gives you that V shape, but then you deal with that negative on the outside. The negative on the outside is a reflection over the x-axis. So let's start by graphing that parent function. Remember we said it was that v with this line actually has slope 1. So we're basically just cutting these two axes, or these two quadrants in half here, going with a slope 1 and slope -1 that way. Okay, so this is y equals the absolute value of x. Now, when we reflect over the y-axis, this first step here, what happens? Absolutely nothing. And that's true because the absolute value of negative x is equal to the absolute value of x. So that portion of it, the graphs are not different because they are equal functions. So that part doesn't really do anything. This green part here, though, definitely has an impact. We reflected over the x-axis. All that stuff that was above now comes down. So all of these on the left side of the y-axis reflect down here. You still have that same idea of the slope being like cutting through that axis exactly there. Okay, so that green is our g of x that we are looking for.